So now let's talk about how to create those input files. We are gonna need like 4 input files, right? One is for the bathymetry, and then and this bathymetry file is like very important, because if this bathymetry file um, has problems, then the funwave-tvd code is not going to run. Well, it's going to run, but it's going to have instability problems. The solution is going to blow up after just a few kind of time steps or something. It's so the bathymetry file is actually quite important. If the solution is unstable, if the output of the funtvd code actually tells you have a blow up of the solution, then it's possible that the bathymetry input file has problems, right? And then you're going to need the initial conditions, the surface elevation, the eta file, and then the 2 velocity files, the U and V, the 2 horizontal velocities that's needed in the initial conditions. The 3 initial condition files are going to be created by using another code, a sequential code called Geowave. It's this particular file, this particular code. You can download it. This is the sequential code, so it's not a parallel code. And this code is can be compiled by just using a GNU compiler, Gfunction. I'll show you how to actually compile that code and run that code in just a little bit, right? And this particular code for generating the initial conditions used for funwave-tvd only requires one input file, which is the bathymetry. And then it's gonna, when you run this code, it's gonna ask you lots of questions about the tsunami source, right? And then if you answer those questions correctly, then it's gonna create the right initial conditions, right? And then those initial conditions, after you convert the format into the format that's required by funwave-tvd, can be actually used as those initial condition inputs that you specify in that control file, input.txt, right? So so the first thing that we have to do is to actually create the bathymetry file. So how do we actually create the bathymetry file? You can actually create the bathymetry file by using just using a MATLAB script. It's not really that difficult, right? So here is my example, my script for reading this particular file that was downloaded from the web, right? It's a bathymetry file that was downloaded from the web, and then it also comes with some kind of coordinate system, right? And this read georost is actually a MATLAB intrinsic function. If you installed the MATLAB, if you have installed the map tool for the MATLAB version, then you should be able to actually have this particular function called read georost, right? And then you can actually read this ASCII file directly. This ASCII file was downloaded from the data center, a data server from of the internet. And then it also comes with the coordinate system, latitude, longitude, right? So if you call this function, another MATLAB intrinsic function, if you have the map tool installed, right? Geographic grid, right? Put the R in there, and then it's going to create the latitude and longitude, right? And then this latitude and longitude are going to be kind of correspond to the A matrix, which is actually the elevation. And then here, what I'm doing is actually convert those files into double, right? And then flip up and down, because the file that's actually downloaded from the web and read into MATLAB is going to have the highest latitude as the first row, right? And then so the rows are going to be organized from top to bottom instead of from bottom to top, right? From bottom to top is something that's expected by both the Geowave and also funwave, right? So we need to actually flip up and down of the latitude matrix and then the elevation matrix, right? And then what I did was to actually double the number of samples in each of the direction, right? This is doubling the samples once, right? And then doubling twice and doubling 3 times, right? So if you double like 3 times, that's 2 to the 3rd power, that's 8 times, right? So the number of samples is going to be about 8 times of the original. And then this interpolation is by default, it should be linear interpolation, right? Make the grid spacing much smaller. right? The reason that I want to make the grid spacing much smaller is because the wavelength. So the original grid spacing, as downloaded from the raw file, was about 400 meters, right? It's about 400 meters. So if I double the number of samples, it's going to reduce to like 200 meters, right? And then double again, that's going to be 100 meters, right? And then double again, about 50 meters, right? So after I have doubled the sampling interval, sampling the number of samples 3 times, the grid spacing should be about 50 meters, right? And then this kind of grid spacing can make sure that I have about at least more than 10, close to about 20, or 10 to 15 grid points per wavelength, right, that I want to capture. So depending upon what's actually the wavelength, the shortest wavelength of the water wave that you want to actually capture, you have to actually refine the grid accordingly, right? So here I found that if I double the number of samples 3 times, right, I can reduce the grid spacing to about 50 meters, which is enough for me to actually capture the wave. And then so if I make a plot of the raw bathymetry file, it's gonna look like that. Right? I tried to actually put this particular bathymetry file into funwave, right? But the problem is that the code is gonna blow up, so I'm gonna have instability problems, right? So what I did was actually so for this particular input, I have too much of a land. So the green areas are all land, right? But tsunami waves propagates in water. So I try to actually remove much of the land by getting rid of the top portion of the entire kind of bathymetry file, right? And then also some of the bottom portion, right? And then also to the left and right, right? So the area that I actually used for doing my simulation is actually limited to this particular area, much smaller area, right? So after I have rejected much of the land area for my bathymetry file, the code seems to be stable. The funwave-tvd code seems to be stable, right? But don't forget, I also have to actually put the same bathymetry file into Geowave to generate the initial conditions, right? The Geowave doesn't actually complain about instability or anything. But if I have too much of a land area, funwave is going to tell me the solution is going to blow up, right? And then what I have to do is to actually create 2 sets of output files for my MATLAB script, right? The first set of output files are going to be read by funwave-tvd. Funwave-tvd is going to require text or ASCII outputs, right? So here I'm actually restricting my simulation area for funwave to this particular small region. So I0 is not going to start from, so I0 and I1 is going to be the starting and ending index for my kind of refined bathymetry matrix, right? My refined bathymetry matrix is B3, right? And I'm taking a small portion out of it that goes from I0 to I1 and then J0 to J1, right? And then I0 and I1 and J0 and J1 were actually kind of determined by eyeballing a subset, a smaller region outside of this from this bigger bathymetry file, right? And then one of the things that I did was to actually reverse the sign, right? Why do I want to reverse the sign, right? Because of both Geowave and funwave is going to expect a positive depth, which means that those blue areas, right? Those blue areas, which is actually deep inside of the ocean with negative values, right, are supposed to be actually positive inside of the funwave-tvd. And to a certain extent in Geowave. Geowave gives you this choice if the depth is going to be positive or negative, right? But usually the default value is going to be assuming the depth to be positive, right? So if it's below the static sea level, right, then it's supposed to be actually positive instead of negative, right? But the file that we downloaded from the web usually assumes a negative. The file that we downloaded from the web, this particular file is going to assume that the depth that's below the static sea level is going to be negative, right? So we want to actually reverse the sign, reverse the depth, the sign of the depth, right? Negative depth. So that's where we actually change this sign, and then all you have to do is to actually save those bathymetry data. Together with the longitude and latitude for that particular subsection, right? The longitude and latitude are not going to be needed by funwave, but it's still useful for saving it because later on you want to make a plot of the bathymetry data that's actually used for the simulation, right? And that's the bathymetry data that's going to be read by funwave, right? In particular, this is actually the bathymetry data that's going to be read by funwave. So if you don't exactly remember, it's inside of the input.txt file, right? Right, that's this particular bathymetry data file, right? So all I did was actually use that MATLAB script to create that particular bathymetry text file, and then just a copy or kind of a transfer the file to this particular directory on my cluster, right? It's the same file. It's the same ASCII file, right? These two files are not needed to run funwave-tvd. And then to run Geowave to create the initial conditions, I will have to actually write the bathymetry data into a specific format called GRD file. And this GRD file is also a text format. It's a ASCII format, but it's an ASCII format that's kind of specific for a software that's called a server, right? It's a kind of quite a popular plotting software for plotting those kind of two-dimensional or three-dimensional data as surfaces, right? The software is called a server, right? And this particular format is specific for that particular software. And I was able to actually find a MATLAB function, right, on the internet, which is called grd_write, right? So if I wanna open this particular function, right, and this function was actually I found, so it's written by this guy. I found it on by just Googling, right? And then it's going to require you to actually put in the matrix, and then the min and max of the horizontal axis, the min and max of the vertical axis, and then the name of the file, right? So it's going to write out this GRD file that's going to be read by Geowave for generating the initial conditions. And that's pretty much everything that's needed in order to actually create the necessary kind of bathymetry files, both for funwave and also for funwave-tvd and also for Geowave, right? So the next step is to actually run Geowave with this particular bathymetry file as the input. And then Geowave is going to create the initial conditions, and then we can use that initial condition to run funwave-tvd. And that initial condition file has to be converted from the GRD format back into the text format, but that's very easy to do. The reason is because Geowave, the output files generated by Geowave are also in this kind of GRD format, right? So we need to actually do that kind of conversion into a text format so that the output of the Geowave can be read into by funwave-tvd. So next, let's try to actually run Geowave, right? Run Geowave to generate the initial conditions. So Geowave is going to give you a bunch of kind of choices. So here, let's go back to the cluster where I actually have a Geowave that's compiled already. So again, this is on directional now, right? And then I have this particular directory in my Anak Kurakato sort of subdirectory. It's called Geowave, right? So if I go into the Geowave subdirectory, you're going to see the source code that I downloaded from that particular website, this particular website, right, called Applied Fluids, and then Geowave, right. Or you can actually find the Geowave website by just Googling, right? Google Geowave tsunami. So here I'm back on my directory cluster, right? So the entire code is actually inside of this particular kind of Fortran 77 source code file, right? So if you look at the go11.f, you're going to see the traditional Fortran 77 style source code with lots of with lots of comments and lots of documentation about what's actually the purpose of each of the code. The entire code is actually not too long. It's not too long. It's only about 13,000 lines, right? And then the whole calculation is inside of this one file, right? It's not separated into like multiple files. And in order to actually compile this particular source code, it's actually quite simple. So I have a shell script compiling the code, right? It's just got like a one line, and on this Linux cluster, on this Linux operating system, I have to actually specify this particular option, MC mode equals to large. Right? The reason is because this Fortran 77 code is going to open a very large two-dimensional static array, right? And this kind of static array is going to occupy the stack, right? It's not gonna. It's unlike the dynamic array that's allocated on the heap, right? It's gonna be allocated in the stack. And then most of the machine, or most of the kind of old machines before in 1970s or even 1980s have very small kind of a memory space, right, for static for the stack, right. And then and even on modern machines, if you do not specify this kind of a option for the compiler is going to assume the stack size is not too big, is not big enough, right, for this particular run. Why do I say this static array is quite big, right? Because if you look at the source code, you actually have to make changes to the source code to adapt to the size of the bathymetry file. And the parameter that you have to change is this parameter, right? So IQ is going to be the number of grid points in the horizontal direction. In our case, it's going to be longitude, right? 2,560, right? That's the matrix size of a bathymetry kind of output, right? Bathymetry file. And then JQ is going to be the bathymetry file. It's going to be the number of grid points in the vertical y direction, right? 1920, right? So if you actually take a look at the size of the bathymetry file, which is exactly the so here the bathymetry file is actually in here, right? So if it's a soft link grd, it's going to point to this particular input file, right? So if I do a head and like a 4, then you're going to see this particular grd file, which was actually written using my MATLAB code, using my MATLAB script, right? Using this line of my MATLAB script, right? So it's linked to this particular file that's in my inf subdirectory, right? Right. I created that particular file using my MATLAB script and then transferred it to directory to my cluster, and then put a soft link inside of my Geowave subdirectory, right? And then the number of points in the x direction, and then the number of points in the y direction. So those two numbers has to match with the source code. With the source code, it has to be exactly the same number over here, right? And then this change has to be made for every subroutine, right? So it's not just this one location. This is the main subroutine, right? But if you actually go into other subroutines, so suppose all the subroutines are actually written in this same file. So if I do search IQ equals to 2560, right? You can sort of see in every subroutine, this parameter file has to be changed. This parameter line has to be changed, right? So how many subroutines do you have? We have. So the simplest thing to do is to, here I'm actually using the Emacs, editor. So the simplest thing to do is to do this kind of automatic replacement. So for Emacs, you can actually do this kind of query replace. So all I have to do is to actually find IQ equals to AQ equals to 1920, right? Then replace it is the correct number, right? For now, it's 20, 50, 60, and 1920 is like the correct number, right? But if this number is not the correct number, I have to do this kind of automatic query replace, right? The query replace means what? It's going to find the occurrences of this particular string inside of this particular file, and then it's going to replace all those occurrences with the correct. So query replace this with what's going to be my correct number, right? IQ equals to what's going to be my correct number, say it's 25, right? And then JQ equals to 19, right? Suppose that's my correct number, right? If I press enter now, then it's going to do this kind of automatic replacement. Of course, it's going to ask me if I want to replace it, right? All I have to do is to answer yes, like 58 times, and then the whole thing is going to have the correct kind of a static array. Here I'm going to quit the query replace, right? So after I have made this kind of a replacement, all I have to do is to actually run this make.sh, this kind of script. It's going to give a bunch of warnings, but it's okay. And then it's going to generate the binary executable. It's going to be called a.out, right? Of course, you can specify the output file executable file name, right? You don't have to use the a.out. It's completely fine. It doesn't mean, but now you can actually run this particular a.out executable to actually generate the initial conditions based upon the specific tsunami source that you're actually working with, right? So if I run a.out in my current directory, then it's going to go through all the different kind of questions, right? So here I'm going to run Bosniask, right? Type 0 for Bosniask equations, right? I'm going to use a Bosniask, right? And then the bathymetry file name, I have a soft link in my current directory, right? So bathy.grd, that's the name of my soft link, and then it's going to automatically link to. When the code actually reads the bathymetry input file, it's going to automatically read the correct input file instead of the soft link, actually, right? And then one of the things that you have to pay attention to is that the file name cannot be very long, up to 20 characters. Right? 20 characters is like a very short, right? So that's why I created this soft link to make the file name much shorter, right? So it doesn't have the sort of relative path, and the file name is very short, right? And then type 0, if this is a surfer ASCII grid file, right? Surfer ASCII grid file was actually the default kind of file format used by Geowave, right? That's why we actually created that the .grd output from our MATLAB script, right? That's why we created this particular output, right? And then type 0, right? If it's a surfer, right? Type 0, the output is also going to be surfer ASCII grid file, right? And in fact, the code was actually set up in a way that if you enter anything that's other than 0 here, it's going to report an error. So you cannot actually handle other kinds of file format. It can only handle the .grd file format, right? Here it's asking you if the depth is positive or negative, right? So the depth here, because I have actually reversed the sign on in my MATLAB script, right? It's this particular minus sign over here, right? So here so the depth is going to be positive for my bathymetry file, right? So depth is going to be positive, so it's going to be 0 here, right? And then the grid is a grid in meters or decimal degrees, right? This is actually asking you about the the horizontal dimension, right? So it's a two-dimensional grid, right? What's going to be the dimension for horizontal grid spacing? It's asking you about that, right? And in our case, we're actually using this kind of longitude and latitude as our coordinate system. So it's going to be spherical degrees, right? So it's going to be decimal degrees. So it's going to be 4, right? And then, so the depth, so here it's actually asking you the thickness of the water coming from the bathymetry file is actually in meters, right? So that's that depends upon the particular file that you're actually downloading from the web, right? What kind of a bathymetry file that you're actually using, right? So if it's in meters, then you have to tell it it's in meters, so it's going to be 0. Then do I want to smooth the bathymetry, right? But for this particular Geowave is actually set up to run 2 separate subroutines. One is called topics, and this topics is actually the subroutine that's going to generate the initial conditions. And then that initial conditions is going to be fed into another subroutine called funwave, right? And this funwave is a much earlier version, and it's a sequential version of the funwave-tvd, and using a kind of different kind of numerical algorithm. So so what the code is going to do is that it's going to so the earlier version of the funwave, the sequential funwave, the numerical methods also has some kind of tolerance about the smoothness of the bathymetry, right? So if the bathymetry is like too rough, that sequential funwave subroutine is also going to kind of have instability problems. So here it's asking you to actually smooth. Do you want to actually smooth the bathymetry input file, right? So here I'm going to ask it to smooth it, but this because we are not going to run this sequential funwave subroutine, but instead we are going to run this funwave-tvd parallel code, right? So this particular choice doesn't really matter, right? Because we are not going to use that smooth bathymetry as our inputs to the funwave-tvd. But still, I'm just ask it to actually smooth the bathymetry file. So it's going to apply its kind of low pass filter, this kind of two-dimensional low pass filter to it. And then it's asking about the number of numerical wave gauge. Wave gauge is some kind of measurement about the wave height, the water wave height, right? So here I have none. And then Lagrange marker, again, some kind of a point measurement of a water wave. I have none, right? And then the number of tsunami sources. So it allows you to actually construct a very complex tsunami source by superpositions of simple tsunami sources, right? But here we are just going to treat our tsunami source as a single tsunami source. So the number of tsunami sources is just going to be 1. And then it's going to ask me to actually choose the different types of tsunami sources, right? 0 is for co-seismic displacement source. That's more like a earthquake, a big tectonic earthquake, that kind of thing. A translational slide source, that's more like landslide, right? And then rotational slump source, and then subaerial landslide source. Here I'm going to use 3 for the Anak Krakatoa volcanic eruption. I'm going to treat it as some kind of subaerial landslide source, right? So here I'm going to choose 3. You also have a pyroclastic flow source, a design wave train source, that's and then a separate tsunami source. So this also allows you to actually specify your own tsunami source as a separate output, a separate input. Right? And then at the beginning time of tsunami generation, let's just use 0, and then opening the property files and the x-axis of landslide entry at shoreline. So that's the source location. It's going to treat it as some kind of a point source. So XO is going to be the longitude of the landslide source, right? What's going to be my longitude? My longitude is going to be like this, right? 105.423. 105.423, right? That's going to be my longitude, and then my latitude is going to be -6.102. -6.102. That's latitude, right? And then it's going to be the direction of the landslide, right? Maybe I have misunderstood what's actually the kind of a meaning of this particular input. It's asking for counterclockwise angle of north in degrees from grid to top, right? So the entire simulation is actually in the southern hemisphere, right? So my understanding of north is supposed to pointing to the equator, right? That's my understanding of the north. But maybe it's not true, right? Maybe my understanding is wrong. Or maybe this code was actually written just for scenarios in the northern hemisphere, right? But I'm not sure. But here I actually put 90 in there, right? So my understanding is that counterclockwise north, the top of the grid, right? The top of the grid top is supposed to be horizontal, right? So west from west to east, right? Counterclockwise, that's 90 degrees. That's the direction of the north. That's my understanding, right? And I suppose this is actually in terms of degrees, right? So it's in degrees, right? It's not in radians, right? In degrees. So I put 90 in there. And then the counterclockwise angle of failure in degrees from north. And for this particular event, the slump direction is actually 140 degrees counterclockwise, about 140 degrees counterclockwise from north. Again, maybe my understanding of the code is wrong. We have to actually try different kind of angles, see which one actually gives us a reasonable simulation results. And then source description is following this particular kind of reference, right? And then the water depth near the end of the landslide, right? And all those kind of information can be actually gathered by site information, right? Looking at the geology of the landslide site. So what I'm going to do is that I'm going to go to a file that's actually so I have a run.sh, right? So I have a run.sh that's going to list all the inputs, and it's going to call a.out, this particular executable inside of this particular script, and then with all the command line inputs sort of listed in this particular order, right? And this particular kind of so this is 90 degrees, right? 140 degrees, right? So the next number is going to be 400. So the water depth near the end of the landslide is going to be like 400 meters, right? 400 meters. So let me put like 400 meters. And then the landslide volume within water, it's going to be like 0.25 E8, 0.25 E8, right? That's scientific notation. And then the landslide velocity at the shoreline, which is 80 meters. And then the landslide run out length in water, that's like a 2.5 kilometers, right? So 2,025, and then 60 seconds in water, right? And then width is 800, right? And then so it's doing this kind of a sanity check. So it's going to come up with some kind of estimate about the tsunami wavelengths, right? And for this particular funwave subroutine or sequential funwave code that the Geowave is going to call, they have a requirement. The grid size has to be larger, has to be smaller than 1/20th of the smallest wavelength of the tsunami wave, right? But this condition is not really needed if you are running the parallel funwave-tvd code, because it's using a different kind of a numerical kind of a scheme, right? And this stability constraint doesn't really apply to funwave-tvd. So here I'm going to type 0 if I wish to continue. So I'm going to keep on continuing. And then here it's actually creating all the initial conditions. See the u velocity and v velocity are two horizontal velocities. And then the free surface shape, that's eta. That's the eta value. And then by now, you can actually stop running Geowave. You can actually jump out of the Geowave by press Control C. Right. If I press Control C and then look at all the outputs, these three outputs are the ones that we are going to need in order to use as initial conditions for funwave-tvd, right? And that's written in the server GRD file format, right? So all we have to do is to actually convert it into the text file format that's required by funwave-tvd, and then it's gonna allow us to run funwave-tvd. So now let's look at the file conversion. Again, I'm using just a MATLAB script inside of my imp directory. So I have a MATLAB script called grd2 text, right? And it's actually quite simple. We are going to use the grd_read_v2. Again, this is a MATLAB function that I found on the internet to read server GRD files. We found a function for writing GRD files, right? And this is for reading GRD files. So if I take a look at the function, it's written by the same guy, and then it's gonna take the file name as input, and then it's gonna spit out this many outputs, right? The one that we are gonna need is the first output, right? We can forget about all the remaining outputs. We are not gonna use them. So we're gonna read the Geowave surface1.grd file that was created by the Geowave code, right? That's gonna be our eta. That's gonna be our surface elevation initial condition, and then U and V initial conditions are gonna be read from these two files, right? And then once we have finished reading those two files, all we have to do is to actually use the MATLAB save command to save them as ASCII files, right? And then I'm going to save them into the external files directory with this kind of file name, right? And the external files directory is going to be the initial conditions for running my funwave TVD code, right? So if I go back into the spherical subdirectory and then go into the if I look into my external files, and then I should be able to actually see all the initial conditions, right? This file, and then this file, that's the U file, U velocity, and then that's the V velocity, right? And then, of course, the funwave TVD also going to require a text format, ASCII format bathymetry file, which is actually this particular soft link, right? And then if we look at this this soft link, it actually points to this particular text file in my input directory, right? This particular, where's my particular, right? This particular file, right? And this particular file was actually created by my other MATLAB script, right? When I actually saved this particular file, it's the same file, right? I saved this particular file and then transferred it to my cluster. And that's pretty much all the kind of required initial condition inputs, right? So now if I go into my work directory and look at my input.txt file, right? So all the file names are satisfied, right? All the file names are satisfied, right? All of them, right? So now I can actually run this particular parallel funwave TVD code, right? Another thing about this input file is that it seems to me that all the integers has to be written as integers, right? So 2560, you cannot write 2560.0, right? You cannot write it as floating point inputs, right? And then all the floating point inputs has to be written as floating points with a .0 behind it, right? And then for some of the floating point numbers, you cannot actually write it in scientific notation, right? So if you write it as 1.0464 e positive 2, then the code is going to run, but it's going to produce incorrect results, or it's going to produce some kind of instability or something. It doesn't actually report a kind of I/O error, but it's going to produce kind of weird results. Again, it's something that might be related to the specific compiler that I'm using on my cluster. If I switch to a different compiler or different cluster, maybe this kind of problem is not going to happen, right? But at least for the experiments that I've done, scientific notations seems to give me trouble that I don't understand. And then integers has to be written as integers. Floating points has to be written with a decimal point, right? And at this point, all I have to do is to actually submit. So all I have to do is to do qsub run.sh, and then the code is going to run. And then depending upon the job scheduling system, you're going to see two files, right? One is the .er file, the other one is the .ou file, right? ER is for any kind of error output. If the code finishes correctly, then this file is supposed to be empty, right? So these two files was specified in my job script, right? So this is going to be the normal screen dump, right? This is going to be the error output, right? I'm running this code for like 1 hour. I'm requesting for 1 hour, but the code is going to finish in about half an hour, right? And this many resources. If the code actually runs finishes in a normal way, then you're going to see a few. In addition to these two outputs, these two files .er and .ou file, you're going to see a log.txt file. This is a log that's generated by funwave-tvd. It's gonna echo back all the kind of input parameters that was actually used in the input.txt file, and then it's in the end. Now, in the end, it's gonna give you the kind of a time integration. Every time step, it's gonna print out the statistics of the waves of the water waves for every time step. And if there is going to be a kind of numerical instability or anything, it's going to print out at which time step it will blow up, and then what's going to be the amplitude of the water wave that caused this kind of a blow up, right? So that's another output, and then it's going to create a directory called output, right? And this directory called output is also specified by yourself inside of the input.txt file. It's a result folder, the result folder output slash, right? So the output is going to be created inside of this particular subdirectory, right? And this subdirectory is going to contain eta, which is actually the surface elevation of the water wave, right? And then Hmax is sort of the averaged maximum height of the water wave as a function of time. And then the number of files are going to be determined by the number of time steps that you try to actually write out. So our simulation is about half an hour, right? 1800 seconds, right? 1800 seconds, and then plotting interval is going to be 60 seconds. That's every minute, right? So you should be able to actually see 30 files, right? So that's why you have 8 or 30. That's like the maximum. So every minute you're going to write out one file, right? So you're going to see like 30 files. And then in order to, these files are all text files. They are organized as a matrix, right? As a two-dimensional matrix. And then in order to actually make a plot of them, it's actually quite simple. So all you have to do is to actually maybe download them to your local computer and then use MATLAB to load the file, right? That's for the 29th minute, right? And then what you want to do is to actually block out the areas that's occupied by land, right? So dmask is actually the elevation, the bathymetry data, the bathymetry matrix, right? It's actually the bathymetry matrix that we actually created and rolled out to disk. It's so dmask is actually the same as the bathymetry data that's inside that's in the ASCII format. So dmask is actually loaded from which file? was actually loaded from this particular file, right? It was created from the first matrix, right? First script, right? It was this particular file, right? So dmask is actually this particular read from this particular file, right? And then so we're gonna set all the locations where dmask is smaller than 0, which means what? Which means it's land, it's above static sea level, right? We're gonna set all those locations to not a number, and then we can just p color inner, right? And then if we choose the shading interp axis equal axis tight, and then the c-axis range, and then color map, choose the color map that's kind of makes the wave amplitude obvious, and then plot the color bar, right? And that's how you actually